Welcome to Pump Design Lab. Today I want to slow down and build something from the ground up. The three conservation laws that quietly control everything a pump does: mass, momentum, and energy. Instead of memorizing formulas, we're going to treat these laws like three honest questions an accountant would ask about your fluid. Where did the material go? Where did the push go? And where did the energy go? The question nobody asks. When you see a pump equation like A1C1 equals A2C2, it's very tempting to accept it as the formula and move on. But that equation isn't really a pump equation at all. It's an accountant equation. It's just a neat way of saying, whatever goes into this box must come back out, properly counted. To really own this material, you have to take one step back. You have to understand why accountant logic applies to a flowing liquid in the first place. Because fluids don't obey rules just because someone printed them in a textbook. The ancient rule behind everything. Fluids obey rules because of something much older and much simpler. In this universe, nothing is allowed to simply appear or disappear. Not matter, not energy, not motion. If something shows up somewhere, it had to come from somewhere else. If something vanishes from one place, it has to show up somewhere else, maybe in a different form. That's it. That's the core idea behind all of our conservation laws. Once that idea is really inside your head, the three equations stop feeling like three separate topics. They become the same idea asked three different ways. Where did the mass go? Where did the push go? Where did the energy go? In this episode, we'll walk through each of those questions properly, the way you would explain it to a curious junior engineer sitting at your desk. Conservation of mass. Your gut already knows T. Let's start with the simplest one. Conservation of mass. This is a law your gut already understands, even if you never called it by name. Imagine you're standing in the garden with a hose. You put your thumb partly over the opening. Immediately, the water jets out faster. Everyone has seen this since childhood. Very few people stop to ask why it speeds up. Here's the reason. The amount of water leaving that small gap every second has to equal the amount of water arriving from the tap every second. There's no extra room inside the hose for water to pile up and wait. So when you shrink the exit area, the only way to keep the same amount of water per second is for the water to move faster through the smaller opening. That single observation is the entire continuity equation in everyday language. Area shrinks, velocity must rise to keep the flow rate constant. It's not some mystical formula. It's just a fluid version of counting buckets per second. Mass conservation inside the impeller. Now take that same idea into a centrifugal pump. Fluid enters the impeller through a relatively large area. From there, it flows into narrower, twisting passages between the blades as it moves outward toward the volute. At every cross-section on that journey, the same rule applies. Whatever the area is at that station, the velocity must adjust so that the volumetric flow rate stays the same from section to section. For liquids like water, the density is almost constant. So mass flow rate is simply density times area times velocity. And for steady and compressible flow, that product has to be the same at each station. This is why, when you design or analyze an impeller, the very first thing you compute at each radius is velocity from geometry. Before blade angles, before lift or head, you let mass conservation and the passage area tell you how fast the fluid must move there. Mass conservation doesn't care how hard the blades push or how much head the pump produces. It only asks one question. With this much space available right here, how fast does the fluid have to move to get through? Conservation of momentum, where the story gets interesting. Now, let's move to conservation of momentum. This is a law most engineers have seen on paper, but often don't feel in their bones. So we'll build the feeling first. Go back to the hose, but change the situation. This time, bend the hose into an L shape. Turn the water on. You'll notice the hose kicks, tries to straighten, and wants to twist in your hand. Why? The water was traveling in a straight line. The bend forces it to suddenly travel in a different direction. But water doesn't change direction for free, any more than a car mysteriously swerves without a steering input. Something has to push it sideways to make that turn happen. In this case, the pipe wall is doing the pushing. The wall shoves the moving water sideways, forcing it around the bend instead of letting it continue straight. And here is Newton hiding in plain sight. If the pipe pushes on the water to bend it, the water pushes back on the pipe just as hard in the opposite direction. That reaction is the kick you feel, not a vague idea of pressure, but a direct physical response to the water's momentum being forced into a new direction. Impeller blades as controlled bend. Now hold that picture in your mind and look at an impeller blade. An impeller passage is doing exactly what that pipe bend does, but on purpose at high speed and continuously. Fluid enters the blade passage with one relative velocity and angle. We often call that W1. The curved blade surface forces the fluid to leave with a different relative velocity and angle, W2. To make that change happen, the blade has to push on the fluid, just like the L bend had to push on the water. And again, Newton's third law shows up. The fluid pushes back on the blade with equal and opposite force. That reaction force, acting at the blade radius, creates a torque about the shaft. Torque, combined with rotational speed, is shaft power. So the motor isn't fighting some mysterious resistance. It is fighting the reaction force of billions of tiny fluid particles being bent and accelerated by the blades every single rotation. Conservation of momentum is what connects we turned and sped up the flow inside the impeller to this is how much torque and power the shaft must deliver. Euler's equation in spiri. T. This momentum redirection story is the physical origin of Euler's pump equation. We won't derive the full formula here, but you can already sense its shape. Euler's equation simply writes down in mathematical form how much did the tangential component of the fluid's velocity change between inlet and outlet. That tangential change, multiplied by mass flow and radius, gives you the hydraulic torque and the theoretical head the impeller can produce. So when you look at velocity triangles in a pump textbook, you're not staring at abstract geometry. You're looking at a visual description of how the blades are redirecting fluid momentum and how that redirection turns into torque and head. Conservation of energy, what the pump is actually for. Now we come to the third law, conservation of energy. This is the one that matters most to your customer because it eventually shows up as a head versus flow curve on your datasheet. To feel this law, let's first leave fluids and think about a simple mechanical picture. Imagine a ball rolling along a smooth, frictionless track. The track dips down into a valley, then rises back up. As the ball rolls down into the valley, it speeds up. As it climbs out of the valley, it slows down. If you calculate its total energy, the energy from its height plus the energy from its speed, that total never changes anywhere along the track. Height energy turns into speed energy and back again, but nothing is created and nothing is lost. Fluids and their three energy forms. Fluids do the same kind of trade-off, but they have three forms of energy instead of two. A flowing liquid can store energy as pressure by being compressed or squeezed. It can store energy as velocity by moving faster. And it can store energy as elevation by sitting higher in a gravity field. Bernoulli's equation is just a statement that, for an ideal, frictionless flow along a streamline, the sum of those three energies stays constant. Pressure energy plus velocity energy plus elevation energy is fixed, just like the ball's combined height and speed energy. That's why, in a simple pipe without a pump, if the fluid speeds up to a narrower section, the pressure must drop. The total energy per unit weight is fixed, so if one term increases, another must give back. Why high velocity means low pressure. So if you squeeze a fluid through a narrow throat and its velocity rises, something has to pay for that rise. Because the total energy budget stays constant, the pressure at the throat has to fall. This is the whole secret behind a Venturi meter. It's also why, inside a volute or nozzle, you often measure a local pressure drop exactly where the velocity peaks. The fluid is trading pressure energy for velocity energy while keeping the total balance. What a pump does to energy. Now here is the crucial sentence that ties our whole episode together. A centrifugal pump exists, fundamentally, to break this energy stays constant rule on purpose. If you only had fluid and pipes, Bernoulli would tell you the total energy stays the same, minus friction. But when you add a pump, you add an external source of mechanical energy. The motor turns the shaft. The shaft turns the impeller. The impeller does work on the fluid by bending and accelerating it. That momentum change we just talked about. Because of that work, the fluid leaves the pump with more total energy per unit weight than it had when it arrived. That increase in total energy per unit weight is what we call head. Head as energy per unit weight. Head is not a mysterious pump word. It is just a convenient way of saying, this is how much energy we added to each unit of fluid, expressed in meter, so that we don't have to constantly mention density. When you read a pump curve that says 30 meters ahead at this flow rate, it is telling you the energy story. At that operating point, the pump adds enough energy per unit weight to raise the fluid by an equivalent of 30 meter, or to create an equivalent pressure rise, plus whatever is needed to overcome friction in the system. So in energy language, a pump is simply an energy-adding device. Mass conservation tells you how much flows through. Momentum conservation tells you the forces and torque involved. Energy conservation tells you how much useful push you ended up giving the fluid. Putting all three together. Now, let's tie the three laws together in one clear picture. Mass conservation tells you the velocities at each point purely from geometry and flow rate. How fast is the fluid moving here, given this passage area? Momentum conservation tells you the forces on the fluid and the reaction forces on the blades and casing. How hard do we have to shove this fluid to bend and accelerate it this way? Energy conservation tells you the head and the useful outcome for the system. How much energy do we actually manage to add to each unit of fluid? You cannot answer all three questions using only one law. You genuinely need all three applied together to go from this is our blade shape and impeller geometry to this is the head, flow curve, and power draw this pump will produce. In classical pump theory, the link looks like this. Geometry and continuity give you the velocity triangles at inlet and outlet. Momentum conservation applied to those triangles gives you Euler's equation and the theoretical head. Energy conservation plus losses converts that theoretical head into a real pump curve that you can compare with test data and sell to a customer. Closing for the episode. Before you rush into formulas or CFD, take a moment to sit with this story. Mass is about how much goes through. Momentum is about how hard we shove it. Energy is about how much useful push we finally give the fluid. Every serious pump design, performance prediction, and CFD model is just a careful numerical application of these three simple ideas. In the next episode, we'll build directly on this foundation and walk into the velocity triangles and Euler's turbomachinery equation, step by step, so you can see exactly how these conservation laws turn into real pump head. Subscribe to Pump Design Lab.